Happy New Year, everyone. Welcome to the Astronomical Society of Edinburgh. Hope you've all managed to avoid the lurgy. I haven't. You'll hear a few of us coughing, so don't make me laugh. Okay, this is what we've got coming up tonight. We have a few introductory things from me, a few news items, what we've got coming up soon, but also we have the result of our Image of the Year competition 2023. Lots of excitement about who's going to win that one. Our main talk of the evening is Exploring the Dark Universe with the Euclid Space Telescope. Dr. Alex Hall is going to be telling us about that, and Nigel Goodman's going to tell us what's in the sky in January 2024, not 2023. Oh, maybe he is, I don't know. I think it's 2024. Let's start with New Year, sorry. We've got lots of new members. Welcome to our latest members. Peter, Mark, Lawrence, Philip, Chris, Douglas and John, and the memberships peaked at 204 now, which is by far the highest in our 100-year history. And Lawrence was our number 200. Is Lawrence here? No? But are any of the others here as well? Online, okay. Oh. Well, welcome to our new members. It's definitely the first time we've been over 200 in that time. Lawrence is online, good, excellent. Welcome, Lawrence. Next time, if you're in the hall next time, I've got an ASE badge for you for being the number 200. On that note, I do actually have some of these ASE badges, which we've had for a while and I haven't had out recently. So if you'd like one, they are just £5. You can either give Alan, our treasurer, £5. I don't think Alan's here tonight, is he? No, he's not. Or you can go onto our members' website and go to the renewal page. You can actually pay for a badge there. So if you want one, come and get one tonight, and you can pay online afterwards. I'll trust you. And they're very nice. I don't often put my pictures on the background, but this is one from our telescope in Spain, and it's my annual pilgrimage to M42, and you can process the data yourself, because all the data from our Azaro telescope in Spain is online, as you know, so you can use that. But we won't be getting much tonight. That's the picture from our observatory in Spain as of today, which is a bit of heavy snow. But our telescopes are snug inside the observatory. The roof is closed, which is fortunate. And as you know, that is our telescope at the back. It's the biggest one in the place. And this is the view from underneath from our dedicated camera with the two telescopes on. It's a bit of a brick at the moment, that telescope. It got moved into this new observatory, and we've had a few problems with it, as you know. And yesterday was even worse when the camera fell out. The cable snagged and the camera fell out, and something hit the ground. But everything looks to be okay. But we are promised by Pablo that he will go in on Monday and get everything working properly and finish the job off. Don't hold your breath, though, because we've been waiting for this for quite some time. The quadrantid meteors showers peaked the other night. It was the 4th, I think it was. And despite the bad weather, our meteor cameras have picked up quite a few. That one's from, I think that's Pat's camera, that one. That's my south-facing camera. Dennis Baczynski, Talbot Nest, got an awful lot of quadrantids. And this is the radiant map from my north-facing camera. You can see it got 93 quadrantids in a short period of time. You can see all there in orange. And that is my north-facing camera. The bright one is actually a sporadic, not a quadrantid. And those lines to the lower left are planes going in and out of Edinburgh Airport. It is quite a tricky shower to catch because it is such a short, sharp peak. And you can see it peaked on the 3rd and the 4th, and there was nothing much before it, and there's nothing much after it. The gap after it is because it was daylight here, but this is from the UK Meteors network, or UK Meteors as it's called now. But it is quite a bomb as well. This is what we've got coming up. For members, next Wednesday we have our Imaging and Observing Group meeting, and if you're new, that's a really good place to come along and learn about astronomy and observing and imaging. And a lot of people have learned a lot from that, and we share our hints and tips and persuade people to buy telescopes they don't really need, which is not really a good idea. I think I should put a show of hands. Who hasn't bought a ZWOC star this Christmas? Not many haven't. Not many haven't. Somewhere in the USA, I think, telling us on the history of innovations in telescopes. And that's an online-only talk. That will be on Zoom for members and YouTube for visitors. On the 2nd of February, we'll be back here again, listening to Einstein's universe about gravitational wave astronomy from Professor Martin Hendry. So that'll be here. It'll be on Zoom again and YouTube for visitors. On the 16th of February, an online-only talk from Mary McIntyre. Mary gave us a talk on the history of women in astronomy, part 1 last year. This will be part 2 completing that. That's actually really good. And on the 1st of March, here again, we'll be having a members' night, so that will be various short presentations from our members. That's always good fun, and you're welcome to come visit us here. It will be on YouTube, but it'll be on Zoom for members, and it will be here, so visitors are welcome to come here as well. This is what you've all been waiting for, the image of the year 2023. Look at the smiles on the faces now. We had 28 entries. These were images that were taken in 2023. And we had a poll of AAC members. You could vote for one only. And there was a clear winner, 23%. So in reverse order, those are all the images we had entered. I'm not going to go through them all. There's too many for that. But third place was Jamie Shepherd, who will be online, hopefully. And that was his aurora from Glen Ogle. And his second place is Ian Smith, the Pop Balloon Nebula, which it really does look like that. And Ian will be online as well. Well done, Ian and Jamie. And the winner is... Overwhelmingly, it was David Harvey's Horsehead Nebula. That's a really nice image. It's a 2-panel mosaic, so is David online?
He is.
Congratulations, David.
Oh, I'm overwhelmed.
Well, it was voted for by most people, so it was overwhelmingly the winner, so well done. I'm sure Neil will be in touch with you about the prize for that, so well done. David is one of our remote members. He's in Christchurch, Dorset, I think. Is that right? Yeah. Not New Zealand, no. In Dorset. In Dorset, yes. Not that remote. Yeah. Okay. So Dr. Alex Hall, who's going to tell us about the Euclid Space Telescope.
Okay. Well, firstly, thank you for the invitation. It's really a real privilege to come and speak to you today about this very exciting project that I'm involved with called Euclid. So my name is Dr. Alex Hall. I'm a Royal Society University Research Fellow based at the Institute for Astronomy at the Royal Observatory up on Blackford Hill. And for the past few years, my work has almost entirely been dominated by this thing on the left-hand side of the screen, Euclid. So just a quick plan of this talk. So I'm going to start by introducing the Euclid Space Telescope, and then I'm going to explain what is it for, why do we need another space telescope, and try to explain some of the science behind the mission. Then I'm going to present some early results from Euclid, and finally discuss the prospects for the near future. So just a little bit about myself first. So I've been in Edinburgh for over 10 years now. Before that, I did a PhD in astronomy at the Institute of Astronomy at Cambridge. So I've been a postdoctoral researcher at the Institute for quite a few years. From 2022 onwards, I've been funded by the Royal Society as a research fellow. And as of last year, I'm academic staff in the School of Physics and Astronomy. Okay, so Euclid. So slight lag on the screen. It will hopefully pop up in a second. I see it on my laptop, so I'm guessing it's just a... Oh, there it is. Okay. So there it is on the left. So this is in the lab down in Cannes in the south of France. So a few of us were lucky to go down and see it last year. So just a few sort of technical specifications. So Euclid is a European Space Agency mission. It's a 3-mirror Corche telescope. The primary mirror is about 1.2 meters in diameter. So this whole satellite's about 2 meters wide. It's about 4.7 meters tall. There's 2 cameras inside it. I'll talk about those in a second. It weighs about 2 tons. The cost of this thing is probably about 1 billion euros. So the initial kind of influx of funding was €500 million, but when you add up all the costs of the salaries and everything, it's probably more like 1 billion. It's called Euclid because it's named after Euclid of Alexandria. He was an ancient Greek mathematician who lived around 300 BC. And he's most known for this treatise, The Elements, which sets out the axioms of geometry. So until relatively recently, this text was one of the standard texts for teaching geometry. So he sets out all the kind of fundamental principles of straight lines and circles and shapes, rectangles, triangles, and so forth. And the reason it's named after him is because Euclid is trying to measure the geometry of our entire universe. And I'll explain a little bit more about that in a second. Now, Euclid has been launched. It was launched on the 1st of July last year on a SpaceX Falcon 9 rocket. So here's the launch. So it's Cape Canaveral on the east coast of Florida. Beautiful day. So originally it was meant to be launched on a Russian Soyuz rocket, but because of the war in Ukraine, that was impossible. We had issues getting it on the European Ariane rocket as well, but eventually SpaceX came to our rescue and was able to deliver a very timely and economic launch. So there we see it go off into space, east coast of Florida, receding into the distance.
Falcon 9 has successfully lifted off from pad 40 and throttled down to prepare for max Q, which is coming up at T plus 1 minute.
Power and telemetry nominal.
So this is like the work of, this satellite was the work
work
of 20 years of effort, and so to see it being put on a rocket and exploded off into space was
Main engine
quite kind of nerve-wracking. So now we're going to see the first stage separate from the second stage. So this is, okay, there it goes. So first stage is detached. That's the camera on the left, and the right we see the second stage camera. The first stage now falls back to Earth. And one of the reasons that SpaceX Falcon 9 rocket is so economical is because the first stage is reusable.
On the right-hand screen, you can see that the MVAC engine has
So on the left, we've got a
ignited.
camera attached to that first stage.
Trajectories.
We're going to see it fall back. Now let's see what
This
happens.
mission,
So
and
just
that is
jump forward
coming
a
up
bit.
here in just a few seconds, followed by the landing burn about
So this is
20
the Atlantic
seconds
Ocean
after
now.
that.
You can see on the left-hand side. And what you'll see in a second is the landing pad come into view. Got some kind of paddle things sort of using to stabilize the first stage. And down it comes. I think this is absolutely
You can
amazing.
see that the MVAC engine has shut down and the landing burn has begun on the first stage
And we'll get
vehicle.
the view from the landing pad now. I still don't really understand how they managed to do this.
Expected loss of signal, Kate. Nominal orbit insertion.
So, yeah, all
What
credit
an
to the SpaceX people
incredible-
for making that work. Right. So once it was sent off, Euclid travelled about 1 million miles, about 1.5 million kilometers, off to a part of space called Lagrange Point 2, which is a special part of space because it's orbiting around the sun but with the Earth. Okay. This is a really good place to put space telescopes because it's very thermally stable. The Earth and the sun are always in the sort of same part of the sky from the point of view of the telescope. It also means that sort of stray light from the sun and the Earth are always coming from the same direction, so it's quite easy to do astronomy. You just point away from the Earth and sun. So, what's inside Euclid? So, the optical design is sort of shown on the screen, but basically there's 3 mirrors. So the light comes in through the top, it bounces off the primary, hits the secondary, comes through this hole. Here's the primary mirror shown on the left-hand side with 1.2 meter diameter. Goes through various sort of paths inside the satellite. And then it gets split. It gets split into its short wavelengths and its long wavelengths. The long wavelengths go into a camera called NISP, our instructions led by France. And there's a picture of it in the lab. So field of view of this is comparable to VIS, slightly poorer resolution, but it's getting you those near-infrared wavelengths. And those are typically quite difficult to get from the ground because of the interference of the atmosphere. So this kind of sharpness, this like high-resolution imaging that means we've got to put this telescope into space. We've got to go above the atmosphere, free from the distortions that blur out the images, because we want really, really sharp images. I'll explain a bit more about why shortly. So soon after we launched the satellite, we started to get the first images down. So this is just a test image from the VIS camera. So this is very kind of raw, uncalibrated, quite noisy data. So, but here we see the image, the focal plane on the left. The full moon is shown for scale on the right-hand side. So each exposure with this camera is an area just a bit bigger than the full moon. For comparison, the Hubble Space Telescope is shown in that little square there. So we're getting much, much wider areas, but at comparable resolution. So let's just look a bit closer at this image. So let's pick out a square here. So, I mean, this is a huge file. I mean, this is like hundreds of megabytes, lots and lots of pixels. You can zoom in, you can start to see all kinds of details, but we see galaxies, we see stars, we see a lot of defects as well. We see cosmic rays, we see internal reflections in the camera. So there are a lot of detailed sort of stuff, this detailed stuff in this image that we need to understand and correct for. Just to highlight a few particular objects. So we've got a collection of stars on the left here. We see an edge-on galaxy in the middle, a nice face-on spiral galaxy on the right. So, you know, really excellent image quality with a relatively short exposure time. So NISP, again, this is the near-infrared wavelengths. Again, it's an area just a bit bigger than the full moon, but you know, you can really zoom in on this image. You can see exquisite detail, galaxies, stars. You see, again, cosmic ray trails. So this is like a really powerful, the image instruments are working really well. This is what we established. So Euclid is a fairly kind of purpose-built experiment. It's going to do a survey of almost the entire accessible extragalactic sky. So that amounts to about 1/3 of the whole sky, and it's going to take about 6 years to do that. So this big wide field of view means that in 6 years you can cover, and planes, you end up with about 1/3 of the sky. Okay, so the Euclid collaboration it's an international partnership, so it's a huge international project, mostly European-led. The Euclid Consortium is the group of scientists who are tasked with analyzing this data, so I'm a part of that. There's quite a few of us up at the observatory part of that. But also the European Space Agency, the national space agencies are all funding this, so the funding comes from the member states of ESA. So the UK Space Agency has put a lot of money into this. There's also partnerships with industry. So Thales Alenia Space built the satellite, Airbus Defence and Space have built the telescope and the payload module. And we also have a partnership with NASA as well, who have contributed technology for the near-infrared detectors. In the UK, we've got a leading role. So the UK is like one of the main 3 countries that are involved with this. So France and Italy are the two largest countries who are contributing to this, but after them, it's the UK. So, I mean, we played a leading role in designing this whole mission, designing the VIS instruments, the data analysis, and in particular, I want to highlight Edinburgh's role. So Edinburgh's co-led the mission concept and design. We also lead a lot of the data analysis. We have the UK Science Data Centre based at the observatory, which I'll talk about later in a bit more. And we have sort of leadership positions across this. So Within the UK, Edinburgh is really one of the central places in this mission. And yes, we get a lot of money from the UKSA and from the Government Research Council for Science. Okay, so that was just a sort of quick overview of the telescope and the technology. But I want to talk a bit more about the science. Why are we doing this? What's the point? Why are we spending a billion taxpayers' euros on such a project? So, this is the mission in a nutshell. So this is a cosmology mission. So it's aimed at understanding the universe as a whole. We're not focusing on any particular individual objects or even individual classes of objects so much. We want to know about the whole universe, its broad brush behavior, its statistical properties. And we want to answer these big questions. We want to understand dark energy. I'll explain what that is in a second. We want to understand dark matter. We want to know about the mass of neutrinos, the dark universe. We want to test gravity. But sort of more broadly, we want to know how the universe is evolving. We want to understand the history of the universe, the future of the universe. We want to understand the Big Bang and what happened then. These big, difficult to answer questions. So the reason that we look at so much of the sky is because we're trying to get a kind of statistical, kind of average view of the whole universe in its entirety as a function of time, because we can look further back into the universe. The further back we look, we're looking back into the universe's history because the light from those distant sources has taken that long to get to us. Okay. So this is, it's a difficult concept to get your head around, but the universe is expanding, and it's been expanding ever since the Big Bang. So we think that the universe is about 14 billion years old, and we think that 14 billion years ago, everything we see around us suddenly burst out of something in this sort of cataclysmic event that we don't really understand and that we've called the Big Bang, slightly disparagingly. Now, that sort of primordial state, we think, was sort of fairly featureless. We don't think there are any stars, or we don't even think there are atoms. It takes a long time for the universe to evolve, for the conditions to be right for life. This takes a long time, of course. This takes billions of years. But we don't sort of fully understand the sort of process of this. There's a lot of interesting, fascinating physics at play that we don't really understand. And it's not helped by the fact that most of the stuff in the universe is invisible. Now, this expansion just means that everything is sort of moving apart from each other. And we think this has been happening since the Big Bang. But after the Big Bang happened, that expansion started to, it's always been slowing down. Gravity likes to pull things in together. That sort of inhibits this expansion concept. That all changes about 7 billion years ago. You'll see that this diagram starts to kind of flare outwards on the right-hand side. So time is running from left to right on this picture. Now, what that's trying to represent is that the expansion has started accelerating, getting faster and faster, and we don't understand why this is. This is one of the great unknown questions, not just in astronomy, but in all of physics. Why did the universe start to accelerate in its expansion? Why did it happen then? What was special about that? We've had to include some new substance in our models of the universe called dark energy to explain this, but it doesn't really explain anything. It's just a part of the model that causes this acceleration. But we don't know what dark energy is. So matter, we think, is about 25%. Now, dark matter, it's also invisible. It's also poorly understood. It is fundamentally different to dark energy because dark matter clumps together. Dark matter is like the missing mass that we know has to be there to provide that extra gravity that the luminous matter just can't provide. Without dark matter, a whole host of different astronomical systems just don't make any sense from a physical standpoint. So we think that dark matter fills the universe. We think that it clumps together. I'll show you some pictures of this later. It creates the environment for galaxy formation and galaxy evolution. So if you add everything up, you find that normal matter, so the stuff that makes up stars and planets, everything we see around us, that only accounts for 5% of the whole universe. So this is a huge problem. We've got dark energy, we've got dark matter. The dark universe is 95% of everything that makes up nature. And yet we don't understand. We don't understand it. So we need to learn more about these problems, and that's the main science driver for Euclid. So it's really a purpose-built instrument that's going to make maps of dark matter. Okay? And using those maps, we're going to learn about how the universe is expanding and therefore learn about dark energy. And this will also give us clues about the initial conditions of our universe. Now, the way that we're going to make maps of dark matter, which is very hard because you can't see dark matter, so how are you going to make a map of it? Well, you've got to use what you can see, and what we can see is galaxies. So we have to look firstly beyond our Milky Way galaxy, and we have to go out into deep space. Okay, famous Hubble Deep Field image here. You see beautiful sort of clusters of galaxies stretching right back into the universe's history. So these are sort of the fundamental objects that Euclid is concerned with, and we'll try to measure. Now, if you look at where the galaxies are in the sky, you can make maps like this. So this is just a kind of picture. Every colored dot in this map is a galaxy. And if you sort of look at this, now this is a huge image firstly. This is like 6 billion light years across, 4.5 billion light years wide. You know, it's an unimaginable sort of scale. But you can do this. You know, you could take a big, lots of images. You just mark on where every galaxy is. You start to see patterns like this emerge. You'll see that it's not totally random. There's structure here, okay? So you see these kind of tendril-like structures. You see regions where there's fewer galaxies, regions where there are more galaxies. So this is what is a really powerful way of understanding about how dark matter works, how gravity works, and how the expansion of the universe is happening, because gravity is ultimately sort of forming these clumps. Gravity is the most important force when you talk about galaxies. So as well as looking for where the galaxies are, you can also use another technique called gravitational lensing. So Euclid is basically optimized to do this. So gravitational lensing is another very powerful probe of where the mass in the universe is. It's a relatively new technique. So the sort of technique I'm talking about has only been around for about 20 to 25 years or so. But if you look at, say, a Hubble image of a dense cluster of galaxies like this one, you start to see these strange features. These are gravitational lensing arcs. You can just about see them, these kind of these thin arc-like structures. So this is like strong distortions of very distant galaxies that are behind this foreground cluster of galaxies. And as the light from that distant galaxy has traveled through this dense region of material, its trajectory has been deflected by the gravity of that stuff. So it's not going in a straight line anymore, it's getting bent. And actually, you get these very strong distortions of those background galaxies that give you these extreme kind of arcs. And actually, you also see multiple images. So you see multiple images of the same galaxy where the light from that galaxy has just taken different trajectories to get to us. It's got different paths to get to us. Now, here's another example that's quite nice. So the effect that's going on when you look deep out into the distant universe, right? Because the refraction of light is effectively being done by the gravity of all of the intervening material between us and those distant galaxies. So we can use that effect to learn about the stuff that's doing that, deflecting, most of which is the dark matter. So this is a powerful way of working out where the dark matter is in the universe. So Euclid's going to sort of look at this chunk of the universe, so back to when it was about half its current age. And this sort of spans this period where that expansion is starting to accelerate. So we can effectively make dark matter maps as a function of time. We can see how those maps have been evolving with time. And the kinds of models or theories that we use are typically reliant on computer simulations. And for this, we need big simulations of the entire universe. So I'm just going to show you an animation of one such simulation. So on the left-hand side, I'm showing a chunk of a simulated universe. This is 100 megaparsecs across, so it's about 100 million light years across. It's a 3D box. We're just seeing a slice of it here. The simulation is going to start out in the very early universe, and we're going to track it with time to the present day, and we're going to see how structure has been changing. Now, this is purely sort of dark matter, if you like. There's no stars or galaxies in this simulation. We're just looking at how dark matter evolves, but the dark matter is going to really shape how the galaxies are distributed, because galaxies will ultimately be tracing out where that dark matter is. So let's just see what happens. So in the very early times, things are quite smooth, but as time progresses, you start to see a structure appear. You see dark spots where there's less matter. You see brighter spots where there's a bit more matter. There's a zoom in on the right-hand side. You start to see, you see things falling in. You see these dense regions where there's lots and lots of dark matter and stuff's falling in. And you see this tendril-like pattern emerge. We call this the cosmic web, or the cosmic skeleton sometimes. But it looks a bit like that picture of the galaxies, where the galaxies traced out this kind of this pattern with sort of tendrils and filaments. This is because the galaxies really do trace out that dark matter. And this dark matter is also doing that gravitational lensing. So this sort of pattern is imprinted on the shapes of those galaxies. Okay, so if we can measure the shapes across huge regions of the universe that are comparable to a box like this, then we can get a pretty accurate measurement of how the universe has been expanding. Now, simulations like this, they have unknown sort of inputs. You need to tell the simulation how much dark matter there is, how fast is the universe expanding, what were the initial conditions of the universe. And so by tweaking those parameters, you get different answers out, you get different sort of simulations out, and we just see which one fits the data best, more or less. I'm just going to play this again because I think it's quite cool. I mean, this is a very recent simulation produced by a team based in the Netherlands. But I think it's pretty awesome that you can do this. So this is the kind of thing we're trying to compare with. We're trying to see if our universe really looks like this. Okay. Now, bear in mind, this is invisible. I mean, this is dark matter. This is not visible material. So it's a very difficult measurement to make, to connect the galaxies, the things that we can see, to the stuff that we can't see. But this is why we need such advanced technology in a mission like Euclid. So in a nutshell, we'll take these images, the galaxies will trace out the dark matter, and that's going to tell us about how the universe has been expanding, and that's going to tell us about dark energy. Okay. And we need to do this over the entire sky because we need those big volumes. We need lots and lots of galaxies. Remember, we're going to get 1.5 billion galaxies by the end of this mission because we need statistics. We need lots of galaxies. We need to beat down all that kind of noise. It's a very subtle effect. All these effects I'm talking about, acceleration, dark energy models, all of these kind of difficult things. Some teething problems. So we very quickly learned about the properties of Euclid. And one of the earliest issues was an issue to do with the stability of the telescope. So the typical exposures of Euclid are, it'll take sort of pictures that are like 10-minute long exposures. And it was having difficulties being stable during those exposures. And the images we were getting down looked like that. So pretty useless. But this was thankfully solved after a software update. It turned out there were lots of cosmic rays in the image that were sort of confusing the onboard fine guidance that uses the positions of stars to stay stable. It was getting confused between cosmic rays and stars. But that's been fixed now. Pointing is now very stable. We also had an issue with stray light, where light was getting in through a strange sort of series exposure, but then you also get the resolution to pick out the individual stars. But then you also get the resolution to pick out the individual stars. So again, for comparison, Hubble Space Telescope, the field of view for Hubble is shown in the bottom left, and it's you're going to get a small patch. So there's lots of science being done on this data right now. In particular at the observatory, actually, to try to use this image to learn about the dynamical history of this globular cluster, to try to look for tidal tails, which are the signatures of merger events, try to work out how much dark matter is in this object. But it's ongoing work, so yeah, I can't give you an update about that right now, but it should be sort of public very soon. I think this is my favorite. This is the Perseus cluster of galaxies. So this is a huge galaxy cluster. It's about 250 million light years away. It's lots of galaxies. We're actually looking at the sort of central region of it here. But again, it's a huge image. You know, if you download this, it's something like 250 megabytes. You can really zoom and enhance and go really into this and stare at all these amazing galaxies. So I think that's pretty amazing. Now we've just got a comparison with the same cluster, but image with a ground-based telescope, and now I'm superimposing the Euclid image. And so when you superimpose Euclid onto the ground-based image, you see lots more detail pop out. You see lots more galaxies. The whole thing is bigger and much sharper. So that's the advantage of going into space. You get out of the atmosphere, you see things start to sharpen up quite substantially. This is another really nice one. So this is spiral galaxy. This is IC 342, sometimes called the hidden galaxy. This is one of the largest galaxies in the night sky. So again, remember, this is about the size of the full moon, this whole image, so it gives you a sense of the scale of this thing. It's typically difficult to see because it's quite near the Milky Way plane, so it's typically obscured at optical wavelengths. I think you can see a sort of a smudge with binoculars, I think. But with the near-infrared wavelengths, a lot of that obscuration goes away, and yeah, with the big field of view, you get this really nice picture of this galaxy. I think that's very, very nice to see. We've got another one called NGC 6822. This is an irregular galaxy. This is just really to demonstrate that not all galaxies are pretty and nice spiral arms. This is sort of a boxy thing. I think there's a bar living in there somewhere, but it's just a very nice, again, a very nice image. There's also some interesting substructure. You see the sort of faint purple things in there, sort of nebulae and things. Quite nice to see. And then finally, this is our image of the Horsehead Nebula. Not quite as good as the image of the year that we saw earlier. Makes you think, why did we bother with this? But again, it's nice, isn't it? I mean, you see the filamentary, wispy structure at the top there. And again, this is with a relatively short exposure time. Again, it looks very, very nice. Something I actually discovered in the course of the last few weeks, learning about this actually was discovered by someone from Scotland, Wilhelmina Fleming, born in Dundee, moved to America, and was one of the Harvard computers analyzing the photographic plates and the data from the Harvard Observatory. And so she's actually credited with the discovery of this system. Okay, so just in the final sort of 5-10 minutes then, I just want to talk about the future prospects for Euclid. Sorry. Yeah, so we're about to start full survey operations. I think the survey starts next month, actually. So we've just been in this phase of commissioning and testing. That's been going on. We have these teething problems that I mentioned that have sort of delayed things a little bit. So the actual survey starts in February, and it's going to build up images of the sky. And it's all fairly automated. So once we start the survey, it's sort of all planned out for the next six years. It's a very intricate problem to work out how to cover that area in the time you've got, with the constraints you've got. The satellite, it has to be quite finely positioned. It has to point away from the sun, of course. It's got quite stringent constraints on the angle it can make with the sun, and that limits the parts of the sky it can see at any given time of year. But there's a whole schedule worked out that's going to build up this map of the sky. To give you a sense of the timeline then, and I won't go into this too much detail, but it's a 6-year mission. We might be able to extend that depending on fuel reserves, essentially, is the limiting factor, the little micro thrusters that are required to keep the telescope stable. There'll be public data releases every few years. The first public data release is planned for about 14 months from now, so sort of spring 2025. But the first sort of major public data release, which is 2,500 square degrees of data, and that's all of the imaging, all of the different filters, all of the spectra, all of the sort of ancillary data that characterizes the telescope and characterizes the optics and so forth. That will come in about sort of spring 2025, or sorry, 2026. So about 2 years' time. 2 years after that, there'll be 7,500 square degrees of data released, and then finally, in about 7 years' time from now, we'll have that full 15,000 square degree survey data out. So we're in it for the long haul, if you like. So this is going to be, I won't be able to come back with answers about dark energy and the mysteries of the universe for probably another 6 or 7 years. It takes that long to build up the numbers you need to get these constraints, to get that information. But in the meantime, we'll have all this amazing images coming out as well. This is a huge amount of data as well, I should say. So this is going to be hundreds of petabytes of data that we'll have to analyze. So one of the most challenging parts of this mission is just the technical requirements of analyzing large amounts of data. No one computer, or not even one supercomputer, can actually analyze all of this at the same time. So it has to be spread across 9 different science data centers, each with their own high-performance computing clusters. 8 of those are in Europe, 1's in the USA. The UK one is based at the observatory here in Edinburgh. It's one of the STFC buildings. That's where our team is based. This is all the people at the observatory who are involved with the mission. I think most of these people are involved with the data processing and the management of the computing resources. There's also a lot of us, including myself, who are sort of working more on the science analysis. But a lot of us have been working on this project for many, many years. So just to sort of wrap up, so the end goals, the end goals that we're working towards, we're trying to measure dark energy at the percent level, hugely ambitious aim. And this is to answer these big questions like, is dark energy evolving, or is it static in some sense? So particle physics will predict that the universe should have an acceleration because all the particles in the universe have quantum fluctuations, and the quantum fluctuations kind of give rise to this accelerating expansion. But the problem is that particle physics predicts a much, much larger acceleration than what's observed. So this is a big sort of problem in fundamental physics, is how to reconcile these two things. So we're hoping with Euclid to shed some more light on that problem. It may be connected to the theory of gravity. So we want to answer, does Einstein's general relativity theory hold across the largest distance scales in the universe? We want to really test that theory really stringently, because it may be that this acceleration is connected somehow to the breakdown of Einstein's gravity. I didn't talk too much about neutrinos, but we have this strange particle that we know about called the neutrino. It's not quite massless, but it's very weakly interacting. We know it has a mass, but we don't know what the mass is. But with a cosmology experiment like Euclid, you can actually measure the mass of neutrinos, which is another really exciting science goal for the project. And we want to know what the initial conditions of the universe were. We want to really track back the history of our universe to the Big Bang and ask, what was the universe like? In that sort of computer simulation I showed you, was it really as smooth as what I showed, or was there more to it than that? And again, these are the sorts of questions that we can answer with Euclid. So I'll just put up my concluding slides just there. It's a very ambitious project, and thanks for listening. Thank you.
Thank you, Alex. That's really good, really interesting, and a fascinating project as well. We've got time for some questions, so we'll go to the hall first. If you're on Zoom, can you put your name in the chat? And if you've got any questions on YouTube, put the questions in there as well, and we'll read them out. So have we got any questions here?
Thanks. Just curious, with dark energy, are you looking at it as spatially uniform, varying in time, or are you looking at it as potentially varying in space as well?
So we're mostly considering uniform in space, and then looking for potential time dependence. The sort of the baseline expectation is that it's constant with time, so that we're looking for that sort of time dependence.
So it's the cosmological constant varying with time in the field equations.
Yeah, exactly. Yeah.
Okay, thanks.
Any other questions here? Lee, have we got any questions on Zoom? Nothing yet? Okay. Well, my question is, what is the unique feature of Euclid? Because, I mean, there are space probes out there, there are telescopes that are doing all these things. Why is Euclid going to be the one that does it differently than the other ones?
So Euclid, it's unique because it has that combination of the wide field of view exposures and the high spatial resolution. So that high resolution gives you really accurate measurements of the shapes of galaxies, and that allows you to do this weak gravitational lensing technique very, very effectively, which gives you the dark matter. Okay, and then the wide field of view means you can do that over a large portion of the sky, and you can do this for, therefore, a billion galaxies. So you get the kind of the statistics you need. So it's unique in that sense. I mean, there have been experiments, ground-based experiments that have done similar things, and we're sort of building on top of that. But this is the first time we've ever put something into space to do that kind of experiment. So in terms of, it's a real kind of step change for doing this kind of cosmology experiment from space. Yeah.
And I mean, you're obviously looking at dark energy, dark matter, and that sort of stuff. Presumably the data's going out to other astronomers who are looking for other things. Have other projects stated an interest for what they can do with it?
Yeah, absolutely. So it's primarily a cosmology mission. That's its sort of main goal, but there's a whole host of other astronomy science that can be done with the data. So there's, for example, you can look at the galaxy population. Yeah. That's what we think. We think that dark matter is sort of clumped together, and we think where there are more galaxies, we think there's more dark matter. Dark energy, again, our working hypothesis is that it's smooth and is sort of fills the whole universe and is everywhere, but that's certainly not established as fact. So that's sort of one of the things.
Like what Mike was saying, it's sort of a cosmological constant.
Yeah, exactly. I mean, you could try to test models where dark energy had some kind of inhomogeneity, had sort of spatially varying models. You could try to test that, and that's those sorts of models will be tested with this data. Yeah.
Thanks.
Are there any questions on YouTube?
That was a great talk. Just one question. Do you think this might open up theories for the multiverse and stuff like this?
I mean, people like to think about the multiverse. There are compelling reasons to believe in a multiverse theory. One of them is actually dark energy. There is this sort of idea that the reason that the cosmological constant has the value that it appears to have might be because there are other universes out there that have different values of the cosmological constant, and for some reason those values do not easily permit life to form. Perhaps they're too high, and so the acceleration is too strong. That inhibits maybe the formation of stars in some way, and so there's a sort of idea, well, maybe we're living in this kind of sort of Goldilocks sort of
in January, which we're hoping will be both cold and crisp, and obviously hopefully clear. I think there's some hopes of clear skies this weekend as high pressure starts to move in, and with plenty of darkness. And we are now past the winter solstice, so theoretically, well, not theoretically, in actuality, the hours of darkness are becoming less, but only by minutes each 24 hours. So there's still plenty of time. We've got the hours of darkness on the 1st of the month, a few days ago. We had 12 hours and 13 minutes of darkness, and by the time we go into the middle of the month, on the 15th, there'll be 11 hours and 51 minutes, so a few 15 minutes or so, as well as a few others, with the many iconic sites and imaging targets. I think we're all pretty familiar with them. So this evening, once we've had a look at the broader picture in the sky, I'm going to take a look at another winter constellation, which is often overlooked, and that is Lepus, the Hare. But before we do that, let's take a quick tour of the whole sky, starting in the east. In the mid-month, looking east, Leo and Leo Minor are prominent in the sky, and also becoming visible are Canis Venatici, Cancer, and Lynx. To pick only one of those, Canis Venatici as a constellation, or more likely to say as the asterism, because unless you have really dark skies, it's quite difficult sometimes in the Western world, and certainly in areas of population, to see an entire constellation. You're usually just looking at a common asterism within the constellation. Canis Venatici has only one star brighter than magnitude 3. It's quite close to us. Two stars of the constellation are within 32 light years of Earth. And the brightest star in Canis Venatici is Corcoroli. It contains 5 Messier objects, M3, M51, the Whirlpool Galaxy, M63, the Sunflower Galaxy, M94, the Cat's Eye Galaxy, and M106, a Spiral Galaxy. And I think we have images of all those in our Messier project that the Society has ongoing. There's also a minor meteor shower associated with this constellation, the Canis Venaticids, which takes place in January. So let's turn south, and we're now looking at these iconic constellations that I've already mentioned. Orion, Gemini, and Taurus are dominating the view. Also, there's one of the largest constellations in the sky, Monoceros, is worth a look. It's a very faint constellation, but nevertheless, it's home to a number of notable stars, a number of variable stars, and Plaskett's star, which is one of the most massive binary stars known to us. And the triple star, Beta I have trouble with this, I knew it would, Beta Monocerotis. Monoceros also, which is the constellation stands for the unicorn, Monoceros, single horn. Also contains several interesting deep sky objects, Messier, the open cluster Messier 50, and the Rosette Nebula, which is a favorite target for a number of members of the Society. Also the Christmas Tree Cluster and the Cone Nebula, and Hubble's Variable Nebula, amongst quite a few others. Turning west, we've got Andromeda, Aries, and Triangulum featuring, and of course Andromeda and Triangulum have their famous galaxies, M31 and M33, M31 being the most distant object in the night sky that you can potentially see with the naked eye, and a favorite for star parties and so on. Aries, to pick one of those, it's also a faint constellation. It has just an interesting factoid. It has 5 stars with known planets, but no Messier objects. The brightest star in Aries is Hamal, Alpha Erites. It does have some DSOs, NGCs 772, 1156, and 972, all of which are galaxies. And turning north, looking north, we have Draco, Cepheus, and Ursa's Minor and Major standing out. Draco is, again, another faint constellation that perhaps is missed by people more familiar with the more well-known asterisms. But it's one of the largest constellations in the night sky again. It sort of winds its way around between Ursa Minor and Ursa Major. And Draco, of course, meaning dragon. And it contains only one Messier object, M102, the Spindle Galaxy, which I think Ramsey got an image of just recently. It has a number of other deep sky objects, including NGC 6543, the Cat's Eye Nebula, Able 2218, Galaxy Cluster, ARP 188, Tadpole Galaxy, and NGC 6340, which is a spiral galaxy. So again, a good hunting ground for observers and imagers. So as I mentioned at the start of this section, let's focus in on Lepus. So Lepus, as we can see, nestles below the feet of Orion, and again, it's a faintish constellation. Its brightest star, Arneb, which is a third magnitude star, and that's it there. Arneb is apparently Arabic for hare, and in fact all the main stars of the constellation are around about the third magnitude. So it really, in terms of picking it out and following its contours, you need a moonless night or a dark sky. It's quite easy to locate. As I said, it's nestling below Orion and a bit to the right of Sirius. And given that Rigel and Sirius are two very bright stars, it gives you nice coordinates for finding this particular constellation. It has some worthwhile deep sky objects that often get missed by both observers and imagers. So the first one of these is M79, a globular cluster. I thought I'd throw that one in for our president. And also a nebula, which is a planetary nebula, IC 418, the Spirograph Nebula. We'll talk about all of these in a moment. And then a third one, NGC 1964, which is a rarely imaged galaxy, and a very interesting variable star called Hind's Crimson Star. So let's look at each of those. So first of all, M79, that's a Hubble image. It has a magnitude of about 8. It's 42,000 light years from Earth, and it's unusual in that it's one of the few globular clusters visible in the northern celestial hemisphere's winter. It's often described as having a starfish shape. It was discovered in 1780 by Pierre Méchain, and in that same year, Charles Messier determined its position and included it in his catalogue on December the 17th, 1780. It was first resolved into stars and recognized for what it was as a globular cluster by William Herschel in 1784. Most globulars are grouped around the galactic center, but this is one of the few which are situated in the other hemisphere, i.e., from the point of view of hypothetical observers in the central bulge of our galaxy, Milky Way, it would be on the other side of us. It's about 60,000 years from the galactic center. At this distance, M79's apparent diameter of 9.6 minutes of arc corresponds to a linear extension of about 118 light years across. And another interesting factoid, it is receding from us at about 200 kilometers per second. I can only find one image in the Society of this globular cluster, which was made by Hugh Somerville back in 2021. And let's move on to the spirograph nebula, so called because of the tracework or nice tracery, which looks like the result of using a spirograph. Anybody remember spirographs? Whether or not people with amateur telescopes and cameras could pick that up, I don't know, but that's might be worth a shot. It's magnitude 10.6, so pretty faint, with a central star magnitude 10.1, an apparent diameter of 12 arc seconds, and it lies 5,200 light years from us. And now to the third one, NGC 1964, the galaxy. This galaxy was discovered by William Herschel, again, on the 20th of December, 1784, using his 18.7-inch reflector. I don't think any of us have an 18.7-inch reflector. I may be wrong. His son, John Herschel, observed the galaxy on the 21st of November, 1835, and Dreyer added the galaxy to the new general catalogue, which was published as NGC 1964, which was published in 1888. It's a barred spiral galaxy lying 65 million light years away from Earth. And again, given its apparent dimensions, it means that NGC 1964 is 100,000 light years across. And at its center, like many galaxies, lies a supermassive black hole. The galaxy has two tightly wound inner spiral arms within a disk with a high surface brightness, and two outer, more open spiral arms that originate near the inner ring. The outer arms feature quite a few small hydrogen-2 regions, and it's the main galaxy in a group of galaxies known as the NGC 1964 group, which includes the galaxies NGC 1979, IC 2130, and IC 2137. And finally, we move on to Hind's Crimson Star, and I just think that description that he has there is very apt and quite poetic, really, where he says that it was discovered by a British astronomer, J.R. Hind, in 1845, and it was named the Crimson Star in his honour because he described it as appearing like a drop of blood on a black field. And I'd love to see an image of it. It's a carbon star and a variable star with a long period variable with a variation between 418 and 441 days and a secondary period of about 40 years. It should be quite, it lies between 5,200, it's 5,200 to 7,000 times more luminous than our own sun and has a radius of 500 times that of our own sun. And it should be quite easy to find, given that it is just below the very bright star Rigel. So let's move from deep space and move to our own solar system. And first of all, let's turn our attention to the moon. And we have a lovely image here by Radim of the crater Plato and the Alpine Valley on the moon, which I'm using as my background for this. So these are the phases of the moon for January. The last quarter was yesterday. And we have a new moon on January the 11th, so we're entering the period of the month known as the dark of the moon. We have not so good for people who want to observe or photograph the moon, but great for people who are doing deep sky stuff. The first quarter is on January the 18th, and the full moon towards the end of the month on January the 25th. As usual, the moon will be having several close encounters with other objects in the night sky, planets principally, and I always have a debate with myself as to whether to cover these conjunctions as part of the talking about the moon, or whether to talk about them as part of the planets. So I'm choosing this evening to go with the latter, and we'll talk about these as we consider the planets. And in fact, it was an image recently by April Robertson, which brought to mind the topic of clear-obscure effects, which I'm going to just mention here since we're talking about the moon. And this was the excellent image taken by April, I think using a Dwarf 2, which another member of the society pointed out that she had in fact got an image of the lunar X, and this is the clear-obscure effect, which is caused by the interplay of sunlight and shadow through the changing moon phases, which provides all sorts of opportunities to see imaginary faces, eyes, cities, letters of the alphabet, almost anything you can imagine. The clear-obscure being derived, as you might imagine, from the French words for light and shadow. There are literally dozens of clear-obscure effects visible on the lunar surface, and I'm quite sure that if you spot something that looks interesting, you could make it up and name it for yourself and publish it as another clear-obscure. A bit of a hunt over on the internet will come up with tons of them. So here are some of them. And let's have a look at a couple of these. So this is the eyes of Clavius, which purport to look like a couple of eyes staring out of the darkness of the crater Clavius. And as I said, you can get lots of information on what time of month you need to look at the moon in order to find these effects. And the second one is the face in Alba Tegnius. I've been practicing that one, which is this one here in the crater Alba Tegnius. And on the right-hand side, on the I suppose it is the eastern side of the crater, that looks like the outline of a face to some people. But anyway, it's a good project, and if you enjoy looking at the moon, which is always very rewarding because it's changing all the time, it's the same but it's changing. It's a good project to give yourself, and as I say, you can make up your own list for ticking off. So let's move on to the planets, and here we are. You can see that Mars and Mercury are basically daylight objects in the coming month, and Mercury might be possible to see. I'm not sure that it'll be observable from this latitude, from here, because it will only reach its highest point in the sky during daytime and is no higher than 5 degrees above the horizon. But it's just recently passed its greatest western elongation from the sun, so it will be away from the glare of the sun. And of course, it would be remiss of me not to mention the hazard of looking at objects so close to the sun. So you've got to be very, very careful if you're trying to pick out Mercury, which is an elusive target both for observers and for imagers. Mars has recently passed behind the sun at solar conjunction, so from Edinburgh it's not readily observable since it lies so far south that it will never rise more than 10 degrees above the horizon. So let's look at some of the others, at Jupiter, Saturn, Venus, Uranus and Neptune. Jupiter, Jupiter you can see is a prominent object in the night sky all the way through the month. Saturn is too, but in the early part of the evening. And Uranus and Neptune, again, are well placed, but hardly prominent. So you've got to go looking for those. So we want to look a bit closer at some of these. Let's take a look at Jupiter. And this was a lovely image. There's been some very good images of Jupiter on the website recently. This is a nice one by David Brett. The planet Jupiter is in Aries all month, a magnitude minus 2.64 to minus 2.42. It's got a disk of about 43 arc seconds. From Edinburgh, it's visible from about 4:30 in the evening, 36 degrees above the southeast horizon initially, and then it will reach its highest point, crossing the meridian, at about 7 o'clock at night, 46 degrees above the southern horizon. And it will continue to be observable through to the early hours of the following day, after which it sinks below the western horizon. There are many objects many Jovian objects, moons that transit the disk, and you can use a freeware called WinJupos to predict when those will happen if you're interested in observing or imaging them. And that's the kind of window that you get where you can put in your parameters of date and time, and you can get little film clips of moons crossing the disk and where they'll be. And I think these are quite accurate, so you can use them to plan a night's observing or a night's imaging, and if you want to catch some of these moons going across the disk of Jupiter. And you can download it at that address. So let's look now at Saturn. And here we have a great view of the ringed planet and its Galilean moons, taken again by Radam. Saturn is diminishing as an object for us to look at and photograph, as it will soon pass behind the Sun at solar conjunction. It's in Aquarius at the moment with a magnitude of plus 0.8 and a disk of about 30 degrees. And of course, this year and next year, the rings will start to close up as the aspect of the rings pointing towards us gets narrower. So they will eventually, at some point, I think in 2025, they will disappear, at least for a time, from our point of view. From Edinburgh, it will be visible from about 5 o'clock in the evening, 19 degrees above the southwestern horizon. So you really need a clear horizon, and it doesn't really get a lot better than that, eventually setting at just after 8 o'clock in the evening. And this is the first time I'm going to mention one of these moon encounters. The moon, Saturn, will be 4.5 degrees west of the crescent moon on the 14th of January. Let's move on to Venus. And this is an image by Robert Arnold of the planet, which I think is quite evocative. I should point out that the phase that's shown in this image will not be the phase through the month of January, but it's quite difficult to get features on because Venus is so bright on the disk, but it's worthwhile trying. Venus is in Scorpius, visible as a morning object, as we saw in the first slide of this section, and it will be in gibbous phase, so a bit fatter than the image shown here. From Edinburgh, it's visible in the dawn. It's currently an evening object, visible around about 5:45 in the evening, 43 degrees, so quite high up above the southern horizon. As it gets dark, it'll reach its highest point in the sky at almost 8 o'clock, a minute before 8, 51 degrees above the southern horizon, so well placed. And it will continue to be observable through to about 1 o'clock in the morning, when it eventually sinks to below 21 degrees above the western horizon. It's in the constellation of Aries, and again, it's 2 to 2.3 degrees south of the moon on the 19th of January. And lastly, let's look at Neptune. Neptune is, again, an early evening object. It's in Pisces, magnitude plus 7.9. From Edinburgh, it'll be visible around about 5:45, 29 degrees above the southern horizon as it gets dark, and it will then sink towards the horizon, setting at 20 minutes past 10. Again, it has another encounter with the moon. It will be 1.3 degrees north of the 24% lit moon on the 15th of January. So that's a good guide to finding it. So let's turn our attention to those interstellar wanderers, the comets, and look at the comets that are best seen in January. There's always a lot of comets, but I'm just concentrating on the ones that are best seen. And I would say that 12P Pons-Brooks and 62P Sushin-Shan are the two most popular at the moment. 12P is being tracked at the moment by a number of members of the Society, and we'll take a closer look at both of these in a moment or two. There's some others made up of comet C 2021 S3 Pan-STARRS. And that's interesting because although it's a very faint comet at the moment, it's worth watching for later in the year, because in the autumn there are possibilities, and indeed might even be expectations, that it'll become what's known as a great comet. In other words, with a nice fancy tail and visible to the naked eye. But we'll see what happens. And 144P Kushida, which in December was magnitude 15. Visibility forecasts are not favourable for this comet, but you never know. 144P Kushida is moving from Aries into Taurus through the month. It starts the month 2 arc minutes south of east to the east of Vega, around about the 10th magnitude, although it's had quite a few recent outbursts which have appeared to take it to better than magnitude 9. It will track eastwards, passing 7 degrees south of Deneb on the 21st, and might become a brighter object still at magnitude 8 by the end of the month. So object still at magnitude 8 by the end of the month. So we'll have to keep an eye on that. And 62P Sushin-Shan on this, because it's already past its peak, and as Mark already pointed out, it's a very, very short peak, and there's a gap afterwards, and you get a few strays following on from the peak. But if you were looking for it last night, that was where the radiant is. It was the radiant's 25 degrees altitude in the northeast. They can produce rates of up to 100 meteors per hour, and some fireballs. It's been known to do that, so it's quite productive, albeit over a short period of time. The last quarter moon rose about midnight, so you had a few hours in which to look for meteors. And finally, I'm just going to finish off with an interesting fact about our own Earth, which is that Earth itself on the 3rd of January this week got to perihelion, its closest point in its orbit of the Sun. When it's reached its closest point to the Sun, when it was approximately 3% closer to the sun than it is at aphelion in July. Whether or not you can see the difference, I don't know, but it should be, it might be measurable. Again, another interesting challenge. So, I'll finish with that, and I'll finish with another wonderful image from Pat of a wintry Edinburgh, which I think just epitomizes Edinburgh winters, and say thank you and clear skies.
Thank you, Nigel. Okay, that's it for this evening. We have our next talk online on the 19th of January about innovations in telescope design. There are some drinks behind, even some wine, coffee and tea. There's a bit of a problem with the kitchen, so if anyone would like to help Peter at the end for tidying up, it needs to go downstairs in the lift. But thank you very much.